In this lesson, you will learn to apply the definitions of the median, the altitude, and the perpendicular bisector of a segment. So let's begin with the term median. The word median, just in everyday English, means the middle. So the median of a triangle is a segment from a vertex to the middle or midpoint of the opposite side. And all of these medians for each segment, for each vertex, will meet at one point called the centroid. So here we see a triangle, and the median goes from the vertex and to the midpoint of this side over here. And then the median for this other vertex would go from this vertex over to the midpoint of this segment. And then using the other vertex, the median would go from the vertex to the midpoint, or the middle, of this third segment. And notice they all meet here at one point. This point is what is called the centroid. So that is with an acute angle, or acute triangle. Here's with a right triangle. The median of the first vertex up here at the top goes from there down to the midpoint of this bottom segment. And then from the right segment, or right vertex, it's going to go from here over to this other segment, and that's going to be the midpoint. And then from the right angle, that vertex up to the other side, is going to the middle, or the midpoint. And now we have these three medians, and they meet at this one point called the centroid. And then here's an obtuse triangle. The first median goes from this vertex down to this side, and that's going to be to the midpoint of that side. And then from this other vertex going to the left side, and then from the other vertex to the other side. And notice they all meet at one point here as well, and once again that point is called the centroid. Next we have what is called the altitude. The altitude is a perpendicular segment from a vertex to the line that contains the opposite side. And the altitude meets at a point called the orthocenter. So here with an acute triangle, the altitude goes from the vertex, and it's going to be 90 degrees to this other side over here. So that is called the altitude, which makes sense if you know what altitude means just in everyday English, because if, imagine, a bird or a plane were right here at this vertex, and the question is, what is the altitude? Well, the altitude is the perpendicular distance straight down to the ground. And same idea with triangles as well. Working with the other vertex, the altitude would be from this vertex going to this side, and that's going to be a 90-degree angle here. And then from the third vertex to the other side, we have again another 90-degree angle. And notice all three of the altitudes meet at one point, and that point is called the orthocenter. With the right triangle, the altitude going from this vertex down to the other side has to create a 90-degree angle. Well, notice this line itself, the side, is already created a 90-degree angle. So the side itself would be the altitude for that first vertex. And then with the other vertex going from here, it needs to be a 90-degree angle to this other side. When I do that, notice once again it's going to be this bottom side. So the altitude for this bottom side would be the side itself. And then for the other vertex, so down here at the right angle, going up to the other side, right here is another 90-degree angle. And so for this one, all three altitudes meet, in this case, at the vertex right here at the right angle. So this vertex right there is where they all meet, and that is called the orthocenter. With an obtuse triangle, we need to create 90-degree angles for each vertex. So looking at this first vertex right up here in the top, we are trying to create a 90-degree angle with the other side. Well, the side that we're trying to make a 90-degree angle with is this side right here at the bottom. But notice, if I were to drop the line, it would not meet on the segment. So what I do is I extend the line, like we see with this yellow dotted line, and then drop this 90 degrees. So now here is our 90-degree angle. Now let's look at this vertex right here. So using this vertex, I need to create a 90-degree angle with the opposite side, which would be up here on the top right. And so 90-degree angle with that side would look like this. So now we have this segment. And then using the third vertex right here, I need to create a 90-degree angle with the opposite side, which would be this side right here. So I need to actually extend this one as well, and then drop the 90-degree angle so that we have a 90-degree angle right here. So that would be all three of the altitudes. But now we need to figure out where is the orthocenter. Where do they all meet? So I need to extend each of those three altitudes. So when I extend the three altitudes, I'll now have them all meeting at this point right here. So this point where they all meet is called the orthocenter. Next we have what we call a perpendicular bisector. A perpendicular bisector is a line, ray, or segment that is perpendicular to the segment at its midpoint. And the point where all the bisectors meet is called the circumcenter. So looking at an acute triangle, we see here in red the perpendicular bisector. Because it is perpendicular, or 90 degrees, here with this side, and is cutting that side in half. So this is one perpendicular bisector. Now looking at the left side, I can create a line here that's 90 degrees as well. So this line would be your perpendicular bisector for that side. And the third side, I can draw another perpendicular bisector, where now I have another right angle. And they all meet at this point that we call the circumcenter. Here is a right triangle, and we see the perpendicular bisector for the bottom side. It's 90 degrees with the bottom side, and it cuts that side in half. For the left side, the perpendicular bisector would look like this, 90 degrees, and it's cutting that side in half. And then the third side would look like this, where we have 90-degree angle, and it's cutting that right side in half. And notice, in this case, the circumcenter is going to be right here on the side, on this long side, which, by the way, we call the hypotenuse. And this point right here is the midpoint of that hypotenuse. So a little side note there, the circumcenter of a right triangle will be at the midpoint of the hypotenuse. And now with an obtuse triangle, perpendicular bisector for the bottom segment would be right here, making a 90-degree angle. For this other side, it's going to look like that, where I have a right angle there. And the third side, I have another bisector cutting that side in half. And in this one, they're going to meet way out here. So this point would be called the circumcenter. And on the topic of perpendicular bisector, if you have this picture, so the segment going up and down cuts the segment left to right in half, where this is 90 degrees, and then this side is the same as this side. There's a theorem that says that if a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. Well, because this is a perpendicular bisector, we know that the left side and the right side are going to be congruent, or the same length. So let's just say, for illustration purposes, that each segment were both 4 inches. And then let's draw the line from the point to the endpoints of that segment. So we're trying to prove that this yellow line is congruent with the other yellow line. Well, for sake of illustration, let's say that the distance from the point down to the segment is 3 inches. Then based off this picture, we have a segment congruent to another segment, and then this angle is congruent to this angle. They're both 90 degrees. And then looking at the two triangles, this side is shared with both triangles. So what we have is a side congruent to another side, an angle congruent to an angle, And then this third side that's shared is congruent with the other side for that triangle. So what we have is actually two congruent triangles based off the side angle side postulate. So because the two triangles are congruent, then I can conclude that the corresponding parts of those congruent triangles are congruent. So the yellow lines would therefore be congruent because of CPCTC. Corresponding parts of congruent triangles are congruent. So we just said that if a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. So this theorem we just proved to be true, and the converse is also true, meaning if we switch the if and the then statement, we also have another true theorem. So that's what we did. So instead of saying if a point lies on the perpendicular bisector, we say if a point is equidistant from the endpoints of a segment, then the point lies on the perpendicular bisector. So both theorem and the converse of the theorem are going to be true. And now dealing with angle bisector, kind of the same exact concept, where if we're given this picture, and in this picture we have the angle that's in blue, the yellow line is going to be the bisector, and then we have a red point on the line. The theorem says that if a point lies on the bisector of an angle, then the point is equidistant from the sides of the angle. So we see here the point is on the bisector of the angle. Then according to this theorem, the point is equidistant from the sides. Meaning, if I were to draw a segment that is perpendicular from that point to each of the sides, then that distance will be the same. So it could be both 4 inches, could be any quantity, but the length will be the same. And the converse of this is also going to be true, where if we switch the if and the then statement, we would also have another theorem. And that would say that if a point is equidistant from the sides of an angle, then the point must lie on the bisector of the angle. So we now have 4 different theorems, 2 theorems and their converses, which are also theorems. And that concludes our lesson for today. We will see you next time.